Hello, I'm Célian Boyé. I'm a PhD candidate in the Aerospace Engineering Department of the Universidad Carlos III de Madrid, and I will be presenting the prototype development and the experimental testing of the magnetic arch thruster, which is part of the Zarathustra project. I'll walk you through the motivation behind the project, the evolution of our prototypes, the results from our two main test campaigns, the one in Madrid and the one in Orléans for my research stay, and finally the conclusions and outlooks. The Zarathustra thruster is based on electron cyclotron resonance, or ECR. This principle enables microwave energy to be absorbed by electrons in a magnetic field where the cyclotron frequency matches the injected wave frequency. This leads to highly efficient plasma generation purely through electromagnetic interaction. This approach is electrodless, meaning it avoids the erosion issues common in conventional gridded or all-effect thrusters and opens the doors to long lifetime propulsion systems and flexibility. We first designed, assembled, and ignited two prototypes, one based on a single U-shaped magnetic arch and a cluster of two ECR sources with opposing polarities labeled as the ECR-C1. Both were tested at the EP2 lab, and importantly, we demonstrated that plasma can be instructed from a closed magnetic configuration, which was a critical proof of concept for the magnetic arch design. We introduced several upgrades from the ECR-C1 to the ECR-C2 during 2024. First, the groove-type gas injection system and a pre-chamber were designed to improve flow uniformity and reduce asymmetries. The copper coils responsible for defining the ECR surface were replaced by N42 permanent magnets, simplifying the system and improving thermal robustness. Finally, both sources were mounted on a single alignment plate to minimize geometric misalignment and ensure magnetic symmetry. The Madrid campaign was carried out in a 3.5-meter long vacuum chamber. We tested the last prototype, referred to as the ECR-C2, with master rates going from 2 to 20 SCCM, with microwave powers from 50 to 200 watts, and with a magnetic nozzle core current set at 2 amperes throughout all the measurements. We used 3 electrostatic diagnostics, Langley probe, Faraday cup, and retarding potential analyzer. We simulated the magnetic field lines from the ionization chamber and antenna and validated them with experimental 2D magnetic mapping. Symmetry between the sources was confirmed, and the differences between simulations and experimental data were negligible, meaning the magnetic alignment was successful. Langley probe measurements were carried out along the symmetry axis with x equals 0 and y equals 0 from z equal 50 millimeters to z equal 300 millimeters downstream. About the ion and electron densities now on the left of the screen. The ion density increased with both microwave power and mass flow rate, reaching values up to 10 to the 16th meter to -3. Electron density was systematically lower than the ion one, particularly at low power. This is likely due to the LP model limitations in the presence of flowing magnetized plasma, especially with the OML model. Now, regarding the plasma potential. A steep axial potential drop, about 8 volts, occurred in the first 150 millimeters from the operation point 5 SCCM with 100 watts. Beyond that, the profile flattened, indicating the transition to a quasi-neutral state in the far field. These results confirm that the first magnetic nozzle contributes to axial ion acceleration. The Faraday cup was used to measure the ion current density. We found that at low mass flow rates, like 5 SCCM, we observe off-axis peaks around ±35 degrees, corresponding to 2 separate ion beams. As the flow increased from 10 to 20 SCCM, the central peak strengthened, and it indicates that the plume is merging as background pressure increased. The ion current increased consistently with power and flow. However, asymmetries persisted regardless of the conditions, possibly due to microwave impedance mismatches, uneven gas flow distribution, or slight misalignments between the sources. These results confirm that the cluster plumes can merge and are sensitive to operating parameters and assembly precision. With the RPA, we scanned the plume at several angular positions. We found that the ion energy increased linearly with microwave power. At 5 SCCM, it rose from 27 electron volts at 50 watts to 60 electron volts at 200 watts. At a constant power, increasing the flow rate lowered the ion energy due to more frequent ion-neutral collisions and less energy per particle. The image on the left depicts the IADF, so the ion energy distribution function, measured for 100 watts of microwave power with 5 SCCM of xenon. The IADF is broader for 6 degrees because of the merging of the plumes from each source. Most importantly, the ion energy scaled with the power to mass rate ratio, following a consistent slope of 4/3, which is coherent with literature for ECR sources and thrusters. In Célian, we perform 2D LIF, so laser-induced fluorescence measurements, to obtain velocity results maps of the ions in the XZ plane thanks to the Doppler effect. We tested both the single source and the cluster configurations. Each file has been treated with a line shape modeling algorithm, originally from Vinci, and this one has been improved to determine the optimal ion temperature. This algorithm is used to rule out the Zeeman and Paschen-Bach effects that can pollute the measurements with the presence of magnetic field. As aforementioned, we applied advanced line shape modeling algorithms to interpret the LIF spectra. Surprisingly, though, in the cluster case, the data could not be fit with a single ion population, as can be seen in the image on the right. Only a two population model matched the experimental data. So we found that we have a main population, which is believed to be generated in the ionization chamber of the sources and to be faster in the Z direction overall. And there is a secondary population, which is believed to be formed in the plume by ionization and charge exchange collisions. This population could not be accelerated as much as the main one, so the main population, by the ambipolar field, and has a lower Z direction velocity and a higher X direction velocity. This is an image of the single source firing with high mass flow rates and high position. For a single source, the ion velocity has been probed in the Z and X directions, and the main population, which is formed in the ionization chamber, could be probed everywhere, where the secondary one, with the orange squares and dots, is only probed where the odd electrons are prone to be found, so through the magnetic field lines which are generated around the coaxial termination. As the secondary population could not be probed in the X direction, only the main population in plane velocity is presented here, with the column map on the left and the ion velocity vectors on the right. Ion streamlines are seen to be detached outward from the magnetic field lines, already at the exhaust of the source. This makes sense, as ions are essentially unmagnetized under the magnetic field strength used in this work. However, they essentially become straight downstream for Z greater than 35 millimeters. Similar measurements have been done with the cluster configuration, as you can see here, with the two populations in the Z direction and in the X direction. However, in this scenario, we see that the secondary population seems to be dominant in the arch. These main population ions, as you can see on the left, they remain straight in front of the left part of the source exhaust. For X greater than 60 millimeters, a slight curvature can be seen towards the external part of the ECRC2. The ions which are probed for X inferior than 45 millimeters are drifting towards the symmetry plane to straighten their trajectory in the Z direction for Z greater than 50 millimeters. This behavior could result from the influence of the plasma beam emanating from the opposite source. Some comparisons can be made up upon the differences between the single source and the ECRC2 configurations regarding the main population ion trajectory. The closed-line magnetic topology seems to have a weaker impact on the ion trajectory than the classic diverging magnetic nozzle one. Also, the ion trajectory straightening occurs much closer to the source exhaust plane in the ECRC2. And unlike in the single source configuration, the maximum in-plane velocity is not reached on the coaxial termination central axis in the ECRC2, so in the cluster situation. Now, for the right image, the secondary population expansion is highly divergent. The in-plane velocity increases along the distance from the right source coaxial termination. The ion trajectory follows the magnetic field lines, and even ions generated for X greater than 60 millimeters and originally directing to the external part of the ECRC2, they drift in the direction of the symmetry plane. It is expected to have an analogous population of slow ions in the opposite direction near X equals 0 millimeters, so on the symmetry plane, coming from the other source. However, this population has not been probed near the symmetry plane because of the limited lifetime of the xenon 2 in the probed metastable level. To summarize, the ECRC2 cluster was successfully built, ignited, and tested in two facilities, and a research stay has been done in Orléans in France. The longly probed data confirm high plasma densities and a strong potential drop enabling axial acceleration. The Faraday cup results show plumb merging, and the LPI measurements confirm energy scaling with power-to-flow ratio. The LIF measurements reveal the complex plume structure with overlapping ion population. Now, the next step is to map the plasma potential through the whole plume and not only in the symmetry plane in order to confirm the predictions made out of the LIF measurements. This is now the PhD thesis has been written and is to be submitted during this week. And you can see on the left the magnetic arch thruster firing with a high mass rate of xenon. This work has been presented in the Plasma-Tech 2023 in Lisbon, the UCAS 2023 in Lausanne, and lastly in the IPC 2024 in Toulouse. And a full journal article was published in the Journal of Electric Propulsion in February 2025 alongside Jeremy Navarro and Mario Merino. Thank you for your attention, and I'll be happy to answer any questions.